This is section 10.4 of Honors Algebra 2 on logarithms. Get excited. So let's solve these equations. Number 1, 25 to the x power equals 125. Well, we know how to solve this. As long as I can write both sides with the same base, then I'll be able to set the exponents equal to each other and solve it. So 25 and 125 have a common base of 5. 25 is 5 squared. This is really 5 squared to the x power, and 125 is 5 to the third power. So 5 squared to the x power, then we multiply the powers, it's 5 to the 2x power equals 5 to the third power. Well, then the exponents must be equal, 2x must equal 3, and x equals 3 halves. You know how to solve that equation already. Let's try number 2. 5 to the x power equals 100. Well, wait a second. I can't write 100 with a base of 5. Can I? What do I do? Well, enter logarithms. 5 to the x equals 100 if and only if x equals the log base 5 of 100. So a logarithm is an exponent. Here's how we will define it. If b and n are positive numbers where b is not equal to 1, so that's some positive number that's not 1, then b to the k power equals n if and only if the log base b of n equals k. So that exponent k is the log base b of n. So the base of the exponent, b, is the base of the log. The number on the other side of the equation is the number we're taking the log of. The exponent is what the log is equal to. So we read this as the base b logarithm of n, or simply, more commonly, as the log base b of n. Thus, the log base b of n is the exponent we raise b to in order to get n. So notice that b to the k power equals n implies, since k is the log base b of n, this implies that by substitution, if I substitute log base b of n for k in my equation, I'll have b to the log base b of n power, so b raised to the power of the log base b of n, and that is just n, because b to the k was equal to n. So anytime I have the base of an exponent and the power as a log with the same base, I just get the number I'm taking the log of. So 5 to the power of the log base 5 of 4, since that 5 is the same as that 5, I just get 4, the number I was taking the log of. It's a neat trick. Here are some examples. Log base 2 of 8. That would be the number that I raise 2 to. So what number do I raise 2 to in order to get 8? Well, that would be 3. 2 to the third power is 8. Log base 2 of 1/8. What power do I raise 2 to in order to get 1/8? Well, since 2 to the third is 8, this must be negative 3. A negative exponent will give me the reciprocal. Okay, log base 3 of 81. So what power do I raise 3 to in order to get 81? Well, 3 to the fourth is 81. So the log base 3 of 81 is 4. How about the log base 1/9 of the fourth root of 3? That's a little harder. So let's call this x. And let's rewrite this in exponential form. So I take the base of the log, the 1/9, I raise it to the power of what's on the other side, which is the x, and that has to equal the thing I'm taking the log of, the fourth root of 3. So I can go back and forth between log form and exponential form. And now I can solve this, because 1/9 is 1 over 3 squared, so that's 3 to the negative 2 power. The fourth root of 3 is 3 to the 1/4 power. So 3 to the negative 2 to the x power equals 3 to the 1/4 power. Means 3 to the negative 2x power equals 3 to the 1/4 power. The negative 2x equals 1/4. And x would equal 1/4 divided by negative 2, which is negative 1/8. Number 7. The log base 5 of 5. Okay? What power do I raise 5 to in order to get 5? Well, the first power. The log base 5 of 5 is 1. Therefore, anytime I have the log base b of b, where the thing I'm taking the log of is the same as the base of the log, it will always be 1. Log base b of b is always 1. What the log base 6 of 1? What power do I raise 6 to in order to get 1? 0. Anything to the 0 power is 1. Any positive number to the 0 power is 1. So, this is 0. Therefore, the log base b of 1 is always 0, anytime b is a positive number. Those are two useful properties of logarithms that you'll need to memorize. Number 9. Convert the equation to exponential form. Log base 6 of 36 equals 2. That's true because 6 squared equals 36. So that's its exponential form. Take the base of the log, the 6, that becomes the base of the exponent. The thing I'm taking the log of goes on the other side. And what the log is equal to is the exponent, because remember, the logarithm is the exponent. So notice that both the base of the log, the b, and what we are taking the log of, that capital N, are defined only to be positive numbers. We cannot take the log of a negative number, and we cannot take the log of 0. We will also not let the base of the log be a negative number, or let the base of the log be 0. And to all sorts of problems if we do that, so we will not do that. We'll only deal with positive numbers as the base of the log and positive numbers that we're taking the log of. Logarithms are functions. In fact, they are the inverses of exponential functions. That's why we learned what inverse functions were before we got to this. For example, if f of x equals 2 to the x power, that's an exponential function. How do we find the inverse? Well, we know we can switch the x and the y to find the inverse function. So x would equal 2 to the y power, but then I need to solve that for y. Well, how do I solve that for y if y is in the exponent? Logarithms. This means y equals the log base 2 of x. If I just convert that exponential form to its equivalent logarithmic form, applying the definition of a logarithm. So the inverse function, f inverse of x, must be the log base 2 of x. So if f of x is 2 to the x, f inverse is the log base 2 of x. So every exponential function has an inverse, and that inverse is a logarithmic function. So every logarithmic function has an inverse, and that inverse is an exponential function. We can go backwards. Since they are the inverses of exponential functions, we actually know what the graphs of logarithmic functions are going to look like, because we know that the graphs of inverse functions are symmetric about the line y equals x. So I've graphed the line y equals x on my coordinate plane already. It's the line that with a slope of 1 that goes to the y-intercept of 0. So it cuts diagonally evenly across my Cartesian coordinate plane. I'm going to use that to help me graph y equals the log base 2 of x. So if I can graph y equals 2 to the x, these are going to be symmetric about my red line. So y equals 2 to the x, that's pretty easy to graph. It'll go through the point 0, 1, because when x is 0, y is 1. When x is 1, I've got 2 to the first, and that's 2. When x is 2, I've got 2 squared, and that's 4. So the point 1, 2, the point 2, 4. When x is 3, I've got 2 to the third, and that's 8. When x is negative 1, I've got 1/2. When x is negative 2, I've got 1/4, and so on. And I can sketch my curve like so. Okay. Now, I will graph the inverse, the log base 2 of x. So since they're symmetric about the line y equals x, all I have to do to graph the inverse is just switch the x and y coordinates of the points from the green graph. So if I take the point 0, 1, that means my inverse function is going to have the point 1, 0. So right there. If I take the point 1, 2, my inverse function will have the point 2, 1. 0.24 implies I've got the point 0.42. 3.8 implies I've got the point 0.83. Negative 1 1/2 implies that I've got the point 1/2 negative 1. Negative 2 1/4 implies I've got the point 1/4 negative 2. So here's what the graph of the logarithm looks like. Symmetric about the line y equals x, that red line. Those are mirror images of each other across that line. They are reflections of each other across that line. So let's graph y equals the log base 1/2 of x. So do we remember how to graph y equals 1/2 to the x power? Sure we do. When x is 0, I'll get 1. When x is 1, I'll have 1/2 to the first power, that's 1/2. When x is 2, I'll have 1/4. When x is negative 1, I'll have the point 2 for y. When x is negative 2, 1/2 to the negative 2 power is 2 to the positive 2 power, so that's 4. So negative 2, 4. When x is negative 3, I get 8. My graph of y equals 1/2 to the x power looks like this. Approaching that horizontal asymptote of the x-axis but never quite touching it or crossing it. So now I can graph the inverse, the log function, which is what I really want to graph. So y equals the log base 1/2 of x is going to be the inverse of y equals 1/2 to the x power. So I'll take the point 0, 1, that becomes the point 1, 0. The point negative 1, 2 becomes the point 2, negative 1. The point negative 2, 4 becomes the point 4, negative 2. The point negative 3, 8 becomes the point 8, negative 3. The point 1, 1/2 becomes the point 1/2, 1. The point 2, 1/4 becomes the point 1/4, 2. And this has an asymptote. Just that it's a vertical asymptote of the y-axis. So logarithmic functions, just like this one, have a vertical asymptote. Right there at the y-axis, the line x equals 0. And here's a challenge. Let's graph y equals log base 2 of x minus 4 plus 1. So we're taking the log of x minus 4, then we're adding 1. Well, this is not really that much of a challenge. It's just taking the graph y equals log base 2 of x, and it is shifting it. Shifting it which directions? Well, it is shifting it right 4. So the minus 4 does on the inside of the parentheses. And it's shifting it up 1. That's what the plus 1 does on the outside. So the log base 2 of x, remember what that one looks like. That was the first one we graphed here. Those are the points 1, 0, 2, 1, 4, 2, 1, 0, 2, 1, 4, 2, 8, 3, 1/2, negative 1, so on. So I'm going to take that, I'm going to shift it up 4 into the right, I'm going to shift it right 4 and up 1. Alright, so the point 1, 0, shifting right 4 will be at 4, 0, 5, 0, and up 1 will be at 5, 1. So I'll do these in a different color. 5, 1. The point 2, 1, shifting right 4 will become the point 6, 1. Up 1 will become the point 6, 2. The point 4, 2, shifting right 4 will become the point 8, 2. Shifting up 1 will become the point 8, 3. 0.83, shifting right 4 will become the 0.123, shifting up 1 will become the 0.124. Okay? The point 1/2, negative 1, shifting right 4 will become the 0.4½, negative 1, and up 1 will become the 0.4½, 0. And this is what it's going to look like. Label some points. Notice that the whole graph shifted, and so did the asymptote. It now has a vertical asymptote that was shifted to the right 4. It's now at x equals 4 instead of at x equals 0. Here are your immediate practice problems. 3 problems. Evaluate these 3 logarithms. That is the end of section 10.4.